My name is Shirley Condon and I'm the Vice-Chancellor of the University of Bradford, and I'm very proud of that role. It's my great pleasure to welcome you here this evening to this inaugural lecture. It's a real privilege to have leading global thinkers at our university. And through this lecture series, we've been very keen to share our very best research to engage and inspire you. Our most recent professors are offering enlightening explanations of their own specialist subject areas. They're conducting internationally significant research, which means our academics always have their fingers on the pulse and at the forefront of the latest research findings, emerging trends, and indeed creating emerging trends and translation through impact. And this evening, we celebrate the promotion of Mostafa Mohamed, Professor of Geotechnical Engineering. I'm absolutely delighted that Mostafa will be presenting his inaugural address to you this evening. Mostafa is a colleague that is held in high regard right across our institution and beyond. And I am truly delighted that he is here tonight to present his research to you. Mohamed, I want to give my warm congratulations to you personally on the achievement of your professorship. Many years ago, I don't know how many it was actually, you supported us on a visit, and I was there to Egypt to seek out some international collaborations. And through that visit, I learned that Mostafa is not only a great colleague, a great academic and researcher, but his kindness and friendship and desire to look after his colleagues, in situations when you're not familiar with Egypt, is outstanding. And I really appreciated that support during that visit, Mostafa. I also know that your family are immensely proud of you. Your wife is sat here beaming. We've got to welcome Dr. Azza El-Ghanami, Karim Mazin and Youssef. Have I missed somebody out? No? And a warm welcome to Mostafa's wider family who are joining us online from Egypt this evening. His mother-in-law, Mrs. Samin Ibrahim, and his brother-in-laws, Dr. Ahmed El-Ghanami and Mr. Hisham El-Ghanami and Mr. Ammar El-Ghanami and their families. You're very welcome. So our mission as a university is to drive sustainable social and economic development through our outstanding teaching and research. And this is why we want to celebrate these lectures. Now, achieving net zero emissions is one of the world's greatest issues. As a permanent observer of the COP gatherings, the University of Bradford is in a front row position to observe and contribute as the world strives to end this issue of the problem with climate change. Now, Mostafa is at the front of this initiative. He's at the spearhead of the research. Mostafa joined the university in 2003 as a lecturer in civil engineering, and he had already acquired much valuable practical experience from working as a geotechnical and structural engineer in Egypt, whilst he also pursued an academic career at Cairo University. But his connection with the University of Bradford, in fact, had already begun because he joined us as a lecturer, having a scholarship to pursue a PhD here, whilst he secured a role at Bradford Council as a highway engineer. And I didn't know about that till this week. And I was just saying to Mostafa, we keep getting contact from the local authority to say they want more people like Mostafa to go and work with them as civil engineers in that same way as you did. And now he's enabling that to happen through his teaching and research. Mostafa focuses his research on temperature-driven processes in saturated and partially saturated soils and utilisation of waste materials to stabilise weak and problematic subsurface soils. I'm not an expert on this, but I will be more after the end of this lecture. He's led and been co-investigator on several important funded projects in these areas on solutions for sustainable construction and the utilisation of infrastructure. It's his passion, I know this, to educate and pass on his knowledge that he has made to make a significant mark on Bradford and his students and colleagues. He's a successful track record in supervising PhD students, as well as providing strong leadership for the Department of Civil Engineering. He secured external funding from the Royal Academy of Engineering to appoint a Royal Academy visiting professor and led the development of 4 new programmes in architectural engineering, architectural technology, construction, and project management and digital civil engineering. And some of this has been very recent. Under your leadership, Mostafa, the Civil Engineering Department is ranked 7th across the UK, and thank you for supporting us to get to that position. He has the distinction of being a Fellow of the Institute of Civil Engineers and a Fellow of the Higher Education Academy. And outside life, Mostafa is the Treasurer of the Bradford Arabic School, which he founded with his friends in 2005 as a non-for-profit organisation. And this is registered as a supplementary Sunday school teacher for the Arabic language. What an achievement. Mostafa also enjoys gardening, growing fruits and vegetables. He's a true polymath. I mean, how do you do it? How do you do all these things? You mustn't sleep. So I now invite Professor Mostafa Mohamed to deliver his Bradford Inaugural Lecture. It's up here, towards achieving net zero emissions, opportunities and challenges for the exploitation of geothermal energy for domestic heating. Mostafa.
Thank you, Shirley, for this excellent introduction. And to be honest, I'm really, and to be honest with you, I do feel proud of being at the University of Bradford, working now for almost 20 years, and I joined another 3 years or 4 years since I started my PhD. So all my life in the UK, I spent it in Bradford. The environment in Bradford University, the support which I receive is great, and that's why I'm feeling that I'm excelling in my research. So thank you for enabling us to excel in our work. Today's my inaugural lecture is about net zero and opportunities for geothermal. And before I start my inaugural lecture, I would like to thank you all for coming today for my inaugural lecture. I would like to thank as well those who joined us online from the UK and overseas. I'm really honored today to give this lecture to my seniors, to my family, my colleagues, and my former students and the current students, my colleagues from industry. It's really honor to give you this lecture. And today I would like to take you through my research related to geothermal energy. But before I start talking about geothermal energy, I would like to highlight just some points about net zero. So for a long time, we have been debating about climate change, about carbon emissions. And sometimes I ask myself, can I work out my carbon footprint? I'm not sure how many of us has already considered working out carbon footprint when they travel to London, for example, 200 miles. The carbon emissions is huge. In fact, it is not only just from transportation. We have to consider all carbon emissions from all our activities. And if we consider this, the impact of carbon emissions is significant. And it results in the greenhouse effect. So this trapped air, this trapped temperature in the Earth atmosphere has resulted in a changing of our climate. And it is our activities that led to the change in climate. And it is also for us it is also for us to act and try to rectify the situation. So in terms of impacts, the United Nations have been discussing this for some time, and they have identified 8 areas that they might impact us in terms of climate change, starting from hotter temperatures, severe rainstorms, and I think to some extent we have been experiencing this kind of events right now. So, for example, last year during the summer, the UK recorded the highest temperature ever of 40.6 degrees. I was in Egypt at the time. In fact, when I came back, my friends and the colleagues told me, you have escaped the wave, the heat wave. So it was colder in Egypt, although it was summertime in Egypt. So definitely there is a change in terms of the climate, and for sure we will have to cope with and rectify this change. But also severe weathers, it does occur frequently. So if we don't act now, there will be more frequency and more severity for these events to happen. And as I said, it is the actions upon all of us to try to rectify and address climate change. So it is when it comes to climate change and its effects, we have to work together as governments, all the sectors, people. We need to make sure that we reduce our carbon footprint. We have to prepare for the worst if the temperature or the rise in temperature is not controlled, and we have to adapt to climate change. So it is, unfortunately, the construction industry itself, which we are proud of, and we feel that it makes massive difference in terms of people's health, so the prosperity of societies. It is, I would say, sustainable, environmental unsustainable, or sorry, it is environmentally unfriendly. So it is not friendly in terms of carbon emissions. The construction industry is responsible for 30% of the carbon emissions in the UK, and globally, the construction industry accounts for 40% of the carbon emissions. It is huge. The vast majority of the carbon emissions in the construction industry and the built environment is coming from heating of our buildings. So heating of our buildings accounts for 80% of the carbon emissions, which is almost a quarter of the UK carbon emissions. It is huge. And the majority of this heating is generated from fossil fuels. So we have to act. And the UK government has set an ambitious target to reach net zero by 2050. And also they have interim targets for 78% reduction in carbon emissions by 2035 and 68 by 2030 compared to 1990 base levels. So it is essential that we decarbonize our heating. Our heating of buildings, we need to ensure that it comes from sustainable sources, from low carbon sources. This will require, of course, is we need to ensure that when we construct, we build new homes, we need to make sure that they are sustainable, they are in terms of energy efficiency, they are also, I would say, most important, they use sustainable materials. But in addition, the government strategy is we have to move gradually into the use of mix of low sources, mix of low carbon sources, like heat pumps and domestic heating. Oops. So from 2025, all new homes will have to use alternative heating system, for example, heat pumps. And of course, the government aims to make major expansion in providing heat through district heating. And in Bradford here, we have just recently, they will build a new district heating in Bradford, a major one. So the government, I would say, aims also to install 600,000 heat pumps by 2028. It is a very ambitious target, but this heat pumps is one of the renewable energy technology. And one of them is the ground source heat pump, where I do my research. So the ground source heat pumps, it includes three elements. The source, which is using the ground to provide the thermal energy. It is the heat pump itself and the distribution system inside the house. The heat pump, it is a well-established technology. It is actually similar to refrigeration, the opposite. And so it is established in other European countries. It has been used. Distribution system, it is similar to what we are using currently in our homes. But the research work is required here for the ground system. Is if we wanted to enhance the performance of the heat pumps, we need to develop new systems, innovative systems. We need to develop new construction materials to enhance the performance of the heat pumps. The performance of the heat pumps is, of course, it is defined, or we can work it out by looking at how much heat we can produce, how many kilowatt of heat we can produce with respect to 1 kilowatt of electricity used to run the heat pump. So my research is focused on the ground system. And when we look at the ground system, there are different ways to join it with the ground source heat pumps. It could be closed system, when we use the coolant to circulate the coolant from the heat pump into the ground system and back again to the heat pump. Or it could be open system, when we try to harness heat from open sources like rivers and sewers. It could be installed as shallow heat collectors in the ground, near the ground surface, and in this case, we lay horizontal pipes, or it could be deep in boreholes, and in this case, it becomes vertical ground heat collectors. We can also utilize our foundations, our substructure, and our infrastructure if we can thermally activate them by embedding heat collectors inside the structure. So in fact, all our structures can be thermally activated, and we can start harnessing heat from the ground. Although it is low-grade heat, the heat pump itself will upgrade this low-grade heat and use it to provide the domestic heating and hot water. So my question is, which I put to myself, how can I enhance the performance of heat pumps? And if we can ensure that we enhance the efficiency of heat pumps, then it is likely that it becomes a cost-effective, viable option, and we can improve and enhance the uptake of technology. So it is all about innovation in developing innovative systems so that we can improve the efficiency of the heat pumps. So today, in the rest of my time for my inaugural lecture, I will take you through the research projects which I have managed, led, or contributed to regarding heat recovery from the ground. I will be presenting to you heat recovery at a house scale, heat recovery at a city scale. I will also looking at the use of conductive additive, how to improve the efficiency of heat transfer, and also heat storage materials. So the first two projects. They are part of European funded project called ENERS. This is Innovative Energy Recovery Systems in the Urban Water Cycles. We were 11 partners from academia, industry, and the local authorities. And also, we carried out the research across 6 European countries, and we received €3.25 million from Europe, and we managed 10 demonstration projects. From the UK, we were the University of Bradford and the Kirklees Council. We were 3 academics working on these projects, myself, Professor Simon Tate, and Dr. Alma Schellert, and the 3 research assistants, and 1 PhD student who was asked now. Yeah, thank you, Mohammed, for coming. Just now, Mohammed, congratulations, Mohammed started his senior lecturership at Exeter University 2 weeks ago. So well done, Mohammed. So it is, so the 2 projects which we managed at University of Bradford, one at a house scale. And when we look at the urban water cycle, we look at starting by abstraction of water. This is the storm water, which can be either going to the ground or reservoirs. When it is treated and supplied to our homes, then it is used by ourselves and drained, discharged into the sewer network. So the first project aimed at looking at if we can divert the storm water into the ground and try to harness the heat from the ground. And the second project is how we can harness the heat from the sewer network, because our wastewater is warm enough to extract the heat from. So the first project, thermal energy recovery at a house scale. This is a demonstration project which we have built in Twisbury, not far from Bradford. And the project itself aimed at reduce reliance on energy provider, reduce reliance on the energy, reduce our carbon emissions, reduce our wastewater or draining the water into the sewer network. So we have diverted the storm water from the roofs into the ground, and we combined it with ground heat collectors. So the heat was harnessed from the ground and used to provide the space heating and hot water. During the summer, we also combined it with a passive air conditioning system so that we can harness the excess heat from the bedrooms, provide cold air, and we use the excess heat here to charge the ground with thermal energy. So we heat the ground from our heat in the rooms. So we worked with Kirklees Council to identify a development area. And in this project, of course, Kirklees Council, they are similar to Bradford. They are 500 inhabitants. Luckily, we had a development in Dewsbury. Dewsbury is approximately 67,000 inhabitants. 26% of Dewsbury population, it is within the 10 most deprived in the UK, and the 20% of the houses, they are actually socially rent. So for Dewsbury project, we have been allocated 4 houses, new houses for new development. Each of the houses is 150 square meter. There are 3 floors, 4 bedrooms house, and they have front garden of 30 square meter and the back garden of 45 square meter. And this is provides the first challenge in this project. The small garden area, it wasn't enough. When we look at our ground heat collectors, shallow ones, is generally speaking, will require larger area to ensure that we harness enough heat for the buildings. So we have to come up with a new design for the ground heat collectors. And in this case, we developed compact heat collectors that we can build in the houses. So for the 4 houses, one was control house, which was equipped by a boiler. This is normal gas boiler. And the other 3 houses, we installed 3 new systems. One was one ground heat collector, and the other 2 was double ground heat panels. Water from rainwater was diverted to the ground in 2 houses so that we can assess the improvements it makes to the ground. So the second challenge which we have also faced in this project is the ground condition. So once the houses were assigned to us, we looked at the geotechnical report, and the top ground and actually made ground. It is made out of ceramic pieces, bricks, and rocks, and all sorts of things, as you can see here in a clay matrix, clay silty matrix. So it wasn't appropriate at all to use this material and to have our ground heat collectors within this type of soil. So we have undertaken very comprehensive laboratory experiments to find a replacement soil. So we have done a good number of experiments to look at the hydraulic as well as the thermal properties of materials, and eventually we selected to use fine sand since it can retain the water for up to 200 ml, which will be useful for the ground heat panels, and also reducing it doesn't change much with wetting and drying, which could happen between rainstorms. System was built on site. We have been managing the work on site, overseeing the work on site, and of course we have used replaced the ground soil with sand, fine sand, which was placed in appropriately and controlled way. In all 3 houses, we have used the 350 meter of pipes in the system, so this was a control. And in addition to that, while we are installing the system, we build a very comprehensive monitoring system because we wanted to assess our designs. We wanted to make sure that we can assess the performance of the new systems. So for each of the houses, we had 135 sensors in the ground, I would say in the panels, the heat panels, to check the temperature in the heat panel. Also for groundwater to look at groundwater level, ground temperature, and groundwater level as well, and its temperature. Internally, we have in each of the floors, we have built sensors to measure the temperature and the humidity inside the house. And also externally, we had ambient temperature as well as measuring the energy usage. So it has taken 5 months. We built the system. We were all very happy. Mohammed, myself, Alma, Simon, and colleagues from Kirklees Council, Leanne and Alison. The system, by the summer, all systems were completed, and we had 4 houses, 1 control and 3 with heat pumps, but with different occupancy. So in terms of results, we monitored the house for 1 full year, and it came as we expected in terms of rain. In this year, we had 850 millimeter of precipitation. So we managed to divert 43 meter cubed of rainwater to the ground. In one hand, this ensured that the ground is moist. So it did help with heat transfer, as I will explain later, and also diverting this amount of water from the sewer network. Of course, it reduced the load on the sewer network and reduced the load to treat this water, and of course, help it reduce the cost of treatment. In terms of effect of the rainstorm on the system performance, we have looked at one of the rainstorms in March, and what we can see here is the rain had increased temporarily the temperature in the ground by 1 degree. However, there was a delay of 55 hours between the time of the event and the time when water caused an effect into the ground. And of course, diverting the ground resulted in 5% enhancement to the coefficient of performance. Ground temperature, just to ensure that it is what we did. This is for the control house, and of course the ground has already proved that it is the temperature of the ground in a near zone of the heat panels varies between 7 and 17%. The front was warmer than the back, and this is due to the orientation of the houses, but also from the data there was a significant interaction between the ground temperature and the ambient. Effect of infiltration trench diverting rainwater. It was very clear that from the data the heat panel, it is in fact can harness the heat quicker and faster, which will provide better efficiency. So it did work diverting the rainwater into the ground. It did assist with heat recovery. The most exciting part is the performance. So when we looked at the performance of the heat pump, we can see here that it is a temperature inside the houses was all maintained throughout the year. However, during the months of the summer months, the temperature went up to 27 degrees. And in inspecting this situation, it is on all houses, we realized that the tenants did not turn on the cooling system, so did not engage. And because it was left up to them to whether to use it or not. But in terms of performance, the performance for all three systems, the best one, which was the double panel, was the infiltration trench, where we diverted water, and then the two panels without, and then the single panel. So the single panel did not work well, and of course there is a dip here, which we found later on that it is due to switching off the system for 20 days. In terms of carbon emissions, because this is very, very important as well. At the time when we installed the system, we were aiming to reduce the carbon emissions. So we have done the analysis for the energy usage of electricity and the gas. And of course, we have reduced the total energy consumption because we moved from the use of gas to electricity. However, when we work it out, the carbon emissions for each of the systems, all four houses were neutral. But this is because of, at the time, our electricity generation was mainly from coal, oil, and the gas. So the carbon emissions of electricity generation buzzed onto the heat panel, and hence the system did not make any saving in make any saving in terms of carbon emissions. Having said that, when we look at the data now for 2021 and we use it to predict, we will realize that we are making 40% reduction in carbon emissions. So this proves that ground source heat pumps, it is one of the technologies that, yes, it proves that it works and it reduces our carbon emissions. So this is my first project. The second project which I would like to talk about is modeling the viability of heat recovery at a city scale. This was also part of ENER's project. And in this project, we were partnered with Aquafin, the water company in Belgium, in Antwerp. And at the beginning of the project, we were invited to visit the sewers. In fact, it is a unique opportunity not many gets the opportunity to go down in a sewer pipe. But it was exciting for me with Simon and Mohammed here as well. When we went to the sewers and we have seen how the water is coming out of the houses, collected in the sewer pipe with everything within it. So it was a good opportunity, I would say. I don't know, maybe it is once in a lifetime, you never know. But I would say it is our aim is to look at opportunities here to recover heat from the city of Antwerp, identify locations and optimizing the heat recovery. So we agreed with Aquafin to run field measurement campaign so that our model is unique, it is validated, and we, alongside the field measurements, we have developed a single pipe model, which we will use later on to develop the sewer network model of 3,000 pipe. And then we have created scenarios to look at heat recovery during different seasons within the year. So 7 sites were selected in Antwerp. Antwerp itself, it is similar in population to Bradford, again, 500,000 inhabitants. But we have 3 sites for soil temperature. We measured the ground temperature down to 4 meters. This is the zone where the sewer network laid in. And also we had 2 sites for measuring the in-sewer air wastewater temperature and also the hydraulic, the flow rate. 2 sites in urban area and the 2 sites near the wastewater treatment plant. So this is large sewers. The data which we have captured, and it was very unique. You wouldn't see many data like this in the technical literature. But few observations to make. Near houses, we probably experience less flow in the sewer pipes. So this is one of the urban sewers. It was around 28 meter cubed per hour. So the ground temperature was quite less than the wastewater temperature, which indicated that there is temperature loss going from the in-sewer water to the surrounding soil. In fact, when we looked at upstream and downstream temperature, based on the analysis, there was almost around 4 degrees drop per kilometer on average over the whole year for urban sewers. So there is temperature in the ground, but it is lost to the surroundings. When we considered the large sewers, the ground temperature was more or less balancing with the wastewater temperature, which is giving again to some extent that there is equilibrium happening here between groundwater and soil temperature and wastewater temperature. The temperature at the wastewater treatment plant varies between 9.5 degrees to 21 degrees, and we can look at here. This is exactly the amount of heat which we can harness. We can set the minimum based on the water treatment plant requirement, but there is plenty of heat which we can recover. This is just, I'm presenting to you here today now, just a couple of examples from a single pipe where we try to look at different scenarios for recovering heat from 20 kilowatt up to 500 kilowatt. And this is in May, where it is warm weather, and it proves that we can recover this heat in here from the sewer pipe, from the urban sewer pipe, and we can reclaim this heat within 1 kilometer of the pipe. If we try to recover more heat, I think we will need longer pipes to work with. The second is we considered for the whole city. We have considered part of Antwerp with 80,000 inhabitants, and we looked at different scenarios for wastewater, how we can recover. And in this case, we considered recovering 200 kilowatt from each pipe. So out of the 3,000, there was 288 pipes that can provide with a minimum flow of 25 liters per second. And we set the boundaries, the limits, that the temperature at the wastewater treatment plant doesn't go below 9 degrees. And also in any of the sewer pipes doesn't go below 5 degrees. So this is give us indication that there is only 133 viable options which we can recover heat from throughout the whole year. So in total, this gives us around 207 megawatt hour per day. This is equivalent to providing heat for almost 4,000 homes. So this is just if we consider this catchment of 3,000 pipes, we should be able to recover heat, and we can provide space heating and domestic hot water for almost 4,000 homes. Of course, if we consider January, it will be half this amount because, generally speaking, the temperature is low. But the maximum in a day was 13.4 megawatt, which was obtained between 10 and 11 o'clock in the morning. So this data give us two conclusions. The first one is when we need to recover the heat, we can recover it from the large sewers, which is not near homes. So there is a special mismatch. And the second is the timing mismatch between we can recover at a time when we don't need the heat. So what is next? We'll try to apply it in the UK. In the UK, we have 47,000 of kilometers of sewer pipes. It transports 11 billion liters of warm wastewater. It is estimated that we can recover 390 trillion watt-hour per year of thermal energy. So we are looking at developing novel construction materials to provide inter-seasonal heat storage in the ground. And this work is with Sheffield University, York, and Exeter. This will be submitted for shortly. And the part of the project we are looking at who owns this thermal energy. It is heated by ourselves. We pay for the heating, and we discharge it into the sewer network. So who owns it? And also, do we have economic modeling to ensure that the revenue and we can convince people to uptake of the technology? So it is very interesting, and this is my future next step in terms of work related to the first two projects. Then I'm working also in enhancing the performance of heat recovery using thermally activated structures. Thermally activated structures, as I mentioned earlier, it could be our foundations for our homes. It could be retaining walls. It could be the slabs. It could be even our infrastructures like tunnels. So any embedded structure, any buried structure in the ground can be activated to harness heat from the soil. This work for the utilization of thermally activated structure started probably about 3 decades. They have looked at the optimization, everything it is in terms of ground heat collectors, in terms of coolant, in terms of looking at the configuration. This is everything. There is a lot of research work, but when we look at how heat transfers, of course, it goes from the coolant to the pipe to concrete to the soil. There is heat transfer through different materials, and there is a possibility if we can enhance the thermal properties of these materials, then it is potentially we can improve the efficiency of the system. So my work here is looking at how we can change the properties of the materials so that we can enhance heat recovery from the ground. So I'm looking at two different areas using of conductive additives, and the second one is heat storage materials. With the conductive additives, we're looking at thermally enhanced concrete and thermally enhanced soil, and we applied this in geoenergy piles and geoenergy walls. And also with heat storage materials, we have developed a new BCM ground heat exchanger, and the novel construction materials is underway. So I built very fully instrumented testing rig in the lab for testing pile foundation, I would say model pile and model wall. It is everything. It is captured in terms of temperatures and flow and so on. And we can control groundwater, the level water table inside the tank, so we can simulate different situations. So groundwater level, we want to, from this experimental work, we want to develop effective concrete using conductive additives. We need to optimize the enhancement of the soil and assessing the impact of heat storage. So when it comes to enhancing the thermally enhanced concrete, the first task is, can we enhance the concrete so that we can enhance the thermal behavior without affecting the strength of the concrete? Yes, I would say we looked at optimizing the thermal properties as well as the compressive strength, and it came that when we add the conductive additives like the graphite, it makes a significant contribution to the strength at the beginning, up to 45% without adverse impact on the strength, and we can double the thermal conductivity or thermal properties as well. So 36% came as the optimum. We prepared the sample and we have looked at the stiffness of the concrete as well to make sure that, because in thermally activated structures, the structure itself, it has two functions, the mechanical load as well as the thermal load. So we need to ensure that both are satisfied, so we can deliver both. So it is the stiffness is enhanced as well as the thermally enhanced concrete. It showed better performance in terms of thermal expansion. And when we looked at the performance for piles and walls, the performance improved by 50% for piles and 67% for the walls. When we enhanced the concrete, we were able to increase the heat flux from the structure to the surrounding soil, and as a result of that, the ground itself engaged better with the thermally activated structure. So the temperature in the ground for all structures that's thermally activated was higher than standard concrete. And this is proved that it is, of course, we can, bigger zone can interact with the thermally activated, so we can harness heat from larger zone. The second project, we looked at thermally enhanced soil, and in thermally enhanced soil, we consider adding conductive additives to the soil adjacent to the structure. And in this case, it was very important to find out what would be the appropriate zone around the structure. So we undertaken, I would say, experimental testing here. We carried out experiments to find out and optimize the zone. And from these experiments, we worked out that if we add conductive additive to the soil within 25% of the interaction zone, it should be good enough to transfer the heat. It was important as well, because we are talking here as a soil, it was important to look at the shear strength parameters, how the mechanical load of the soil. And it did prove that it is, of course, the resistance to failure. In this case, it can be improved with the addition of conductive additives up to 15%, but 10% it was the optimum. In terms of performance, the thermal properties of the thermal enhanced, it is doubled, it's more than doubled as well. And in terms of performance of the system, the system performance, the amount of heat that we are able to harness from the ground increased, I would say, by almost 30% in case of piles piles with thermally activated soil, with enhanced soil. So the improvement in terms of adding additives optimum value is 10% conductive additives. It was effective enough to enhance the thermal properties of the soil, and enhancement of 80% was achieved for the piles, and 100% was achieved for the walls. In terms of the soil, here we always have a problem when we have these structures, is the thermal resistance, contact thermal resistance. And in this case, by enhancing the soil adjacent to the structure, we proved that it is the soil temperature is more or less exactly the same here when we added the graphite to the structure. So this is it was quite important to realize that in enhancing the soil adjacent to the structure, it improves the heat transfer from the structure to the surrounding soil. And also we look here that it is a better performance in terms of engaging more soil, enlarging the soil that it engages and we can harness from. This is another project which we worked on, is developing BCM heat exchanger. And in this case, we are using heat storage around the heat exchanger and we looked at the performance of the system under cyclic loading or heating and cooling. And it proves that when we use heat storage material around the heat exchanger, encapsulated around the heat exchanger, there is a significant improvement of almost 75 in heating and 43 in cooling. In addition to that, when we use the storage, thermally storage material inside our piles, our thermally activated structure, we will reduce the soil interference because we can store the heat and we can also harness this heat. In terms of walls, this is again similar performance, but less. We have used a different in this project. We used a different heat storage material, and the performance for the walls, it was 43 improvement and 32 in cooling. The soil zone, the interaction of the soil zone here, it was much less in terms of heat transfer in soils. The last one, which is I'm really proud of, and I think there's significant development and potential, is developing, I would say, novel BCM aggregates where we can store and release heat from the aggregates. So we are currently undertaking experimentations in the use of lightweight aggregates and also man-made and natural aggregates, vascular aggregates, trying to impregnate it with phase change material so that we can use it in construction, in the ground, and also in structures. There have been some work being done, but is not successful. So far, we have been successful in saturating the aggregates with the PCM and sealing it properly. We have been, I would say, carrying out the investigations, and from what we have done, we have seen significant improvement in terms of specific heat, the amount of heat which we can store in the ground and release from the ground. Because since we are talking about these materials that it will be used as construction materials, it is important that we look at the mechanical behavior as well as the thermal behavior. So mechanically, there is improvement in terms of the mechanical behavior, this one here. In terms of density and permeability, flow of water, it was quite less because the material itself is lighter, but it has and bigger, so it is improved the permeability coefficient. In terms of efficiency, significant enhancement from our trial tests. There was significant enhancement in terms of the performance of the pile and the walls was achieved. So what is next for me is I'm looking for upscaling the process. We want to deploy the material, this novel construction into different structures. So we are looking at upscaling of the material. We're looking at optimizing the system performance based on coupling conductive additives as well as heat storage materials. We want to run full-scale tests to prove the concept of the work. And I want to investigate the thermal cycling as well, because if we have these materials, this heat storage materials in the ground and also in the structures, we need to make sure that it is stable for the lifetime of the structure. So it is important that we deploy the novel aggregates to real projects. So this is what I would like to cover, but before I finish, I would like to acknowledge the hard work of all my PhD students who completed with me, in particular Mohammed for this project. I have 3 themes, as Shirley mentioned earlier: thermal recovery and also stabilization of soils using waste materials, and also looking at soil structure interactions. So of all my completed PhD students and also current PhD students, I would like to acknowledge the work of Omar. Abu Bakr contributed to the project, and Mohammed as well here is working and developing this area. So thank you for listening. I hope you enjoyed the time, and happy to take any questions.
Thank you, Mostafa. An excellent talk. Thank you very much.
Thank you, Martin.
My name is Martin Priest. I'm the Dean of the Faculty of Engineering and Informatics here at the University of Bradford, and it's my honour to chair this part of the evening, which is around your questions and perhaps even suggestions and comments to Mostafa. We will take some from the room, and then we'll see if people want to ask questions online. So does anybody in the room want to start? The gentleman here.
Yes.
What is the solution for the cost?
Okay. If we enhance the performance, so what will happen? We will reduce the running cost of the system. So even if there is a capital cost at the beginning, we should be able to gain it. So this is definitely. So my research is looking at the performance, so that we can increase the uptake of the technology.
But capex for the individual household is going to be huge. Yeah. How are people going to afford this?
The government, I believe the government has already providing subsidies for the heat pumps for certain groups. But if in the future, anyway, from 2025, all new built homes will have to be using alternative. There will be no boilers. So it will be incorporated in the cost of the construction.
Owen Green, Peace Studies International Development. Thanks very much. So I've got 2 linked questions. It's a fascinating talk. It's really interesting to hear. Thanks. So as I hear your framing, the area where the technology and knowledge isn't so mature is the actual heat exchange in the soil. It's the heat retention, not the heat pumps themselves.
No. Yeah.
So within that framework, I just wondered two questions really. One is how mature do you feel that the side of the heat pump technology that you've been dealing with is? I mean, 45%, 75% increases above the normal. That's pretty big, you know.
Yeah.
But presumably, the question is how rapidly you think that's going to increase as knowledge goes, or whether we've got some prospect of having a reasonable understanding of, maturity in that understanding by within the 5 years that we need in order to start reaching those targets. That's the first question. And the second question is, obviously British law is relating to new build, and obviously the biggest challenge is how to deal with existing infrastructure. And so I just wonder, obviously you've answered that question in relation to cities, sewers and so on. That's not retroactive, but in terms of fitting it to existing housing stock, do you have any comments about affordability? You read in the papers that it's quite an expensive and a large engineering process, and I just wonder whether or not you can see how you'd comment on the trends in that dimension too.
Thank you for your questions. They are excellent questions. The first question, I think based on the experimentations that we have undertaken, it proves that the system will be improved, but we need to further work is definitely required. to ensure that we optimize the whole system. Secondly, is with regarding to the first point, is we have to undertake full-scale testing. If we want to make sure that it proves that it works, and not only for short period, for long periods, we have to build it in a full scale and run the test. So hopefully, I'm in negotiation, I would say, working with colleagues from Norway and from Birmingham University. We are trying to develop a project. So hopefully this will be in a full scale with the industry. With regarding to the second point, it is out of my expertise, but I will rely on colleagues from Faculty of Management who are collaborating with me at the moment in a project, and hopefully we'll be looking at the revenue and the cost in terms of modeling the investment and return. So it is, I would say it is hopefully they are in the same faculty. Hopefully when we start the project, I will be excited to invite you as well to contribute. So thank you for your question.
Thank you very much. I'm a PhD student, last year PhD student. So I wonder, you have said that 347,000 pipelines underground pipelines in the UK.
So and 340,000 kilometers.
Kilometers.
Yes.
Sorry. And every day it was about 11 billion liters water. So is it possible to change the whole system by your new system, you know?
I think it will be impossible. As, this is the systems in the UK. Generally speaking, when we compare in another project, in the UK, we always, if there is a problem in the system, we try to fix it. In other countries in Europe, they replace it. So there is a big difference. So I don't think it is in the UK we'll be able to change it.
There was a question at the front here.
Yeah.
Thank you for your presentation. Yes. You said that 30% of the construction involves the carbon emission, right? So my question is, if we are converting every single house into low carbon emission like this, so that also involves the construction, right? Because you will construct all the structure for using the heat from the soil. How sustainable are the materials that you will be using, and how you will control the construction which will happen for converting all these houses in terms of carbon emission?
Are you talking about new or existing?
Yeah, it's the whole. If you deploy all of these in the whole UK, how will we control the carbon emissions emitting from the construction that will be performed by applying all of these methods?
Okay, so if I clarify it, the construction industry produces 30% of the whole UK carbon emissions, but 80% of that is due to heating. The other 20 is due to other aspects, which are saying that using of materials and so on. So both have to go hand in hand in terms of resourcing sustainable materials, improving that the production of, for example, of cement. We look at the alternatives. So it is, as you might know, 1 ton of cement produces 1 ton of carbon dioxide. So it is. So if we can change the situation for other materials and also move towards low carbon heating, then the whole construction, the whole built environment will produce much less carbon emissions. So thank you.
Question at the back there?
Yeah, Peter.
Thank you, Mostafa. That was great. Now, one of the other ways of reducing carbon dioxide in the atmosphere, of course, is to plant trees, and trees have roots. So when we've got in groundwater heat exchangers, are they safe against root damage, or do we need to protect them against root damage?
This is excellent question, Peter, because this is what happened in Dewsbury when we installed the system. The panels was around 2.35 meters from the finished ground surface and 1.85. We stipulated in our technical report that no planting of any trees in the back garden should happen. So it is, yes, it is potentially will be damaging, but if we are building the system, we have to ensure that the trees are outside the zone which we utilize for harnessing of heat.
Thank you very much. Pleasure to see you again. So my thought was, with the ground source array, could you divert the domestic waste water around your array? So you don't need to go to the wastewater treatment work. You can use the array that you're proposing already. Has that been considered? What's been said?
Okay, thank you for the question. It is a good idea. I would say it hasn't been considered in the project. In fact, in our project, but it was considered in Belgium, for example. We have Valerie. They have the demonstration project for heating of block of flats, which was near a hospital. So the hospital produced significant amount of wastewater daily. So try to divert, use the sewer water to harness the heat from it through recycling of this water in the heat exchanger and heat pumps. But in your, if you are looking at ground heat collectors, that it is laid at shallow depths in the back garden or front garden, possibly or practically, I'm not sure. What we thought about at the time, if we can have a heat panel inside the manhole. So if you can have something in the manhole, we can extract the heat as it comes. But the problem is, with water flowing, it doesn't stay in the manhole. So you need to have a capacity of water so that it gives the time to harness the heat for using the heat panel. Amir.
My name's Amir Hussain. I thought it was fantastic and really, really exciting to see this happening here. I guess my question relates to its application and to what extent you or the university is planning to implement this into the real world, maybe with a private sector partner presenting this kind of information in a much more digestible way that the sector as a whole and development sector can start to understand this in a really clear and concise way and be able to encourage that kind of uptake of this application, because it still feels very much like it's at a research phase. But at what point and what's that longer term view for this in terms of implementing it in a wider context?
Yes, excellent. To be honest, I'm looking forward to collaborate with the industry. Yorkshire Water, we have meeting on Thursday with Yorkshire Water. Hopefully, they will sign up. I met with also Andrew from One Energy for district heating. So hopefully, we can collaborate in future. But definitely there is opportunity without transforming and transferring the knowledge from our research into real world. I don't think there will be much benefit. We can do the work and the research work in the labs, but we have to somehow to build it in real life and making sure that the industry benefits from our research. So I'm looking forward to collaboration with the industry, and I will be keen to collaborate with potential partners.
And if we think of the more traditional side of construction engineering, the structures, a lot of work goes on there, international standards and design guides. How far away do you think this work is from appearing in that type of user information?
Part of the research which we plan to do is to develop guidelines, but these guidelines sometimes we inform, for example, in previous research work, we can inform the standards, we can inform the industry, but it is not always the case. So it is, yes, but it is definitely, it is a possibility that we can, the guidelines from the research work will help the industry to change.
There's a question over here, Jamal.
I think I can ask you. Thank you so much, Mostafa, for the presentation. Very interesting topic to me. But I'm just wondering, one of the areas that you mentioned is the embedding the system, the thermal, geothermal system within the structure of the building. So as far as I know, the system life is about 25 years. And we're expecting the building, especially the new structures, to live 56 years. So how about the maintenance side of this? That already costs fortunate if you're going to dig into this foundation and all this, or even the walls, all these things. This is one of the questions. The other thing is probably currently the funds available for heat pumps is only for the air source heat pumps, as they cost around 10,000 maximum. But for the ground source heat pumps, that's quite expensive. As far as I know, it's over 30 grand. So who is going to afford this? And looking at the return of the investment, really, that's going to be 100 years for private sector. So especially the challenge for people, there's no fund available to cover the geothermal. I have lots of questions about probably these two.
These are valid questions, Jamal. With regarding to the first question, I think once we build the system, there is no maintenance required. If you have the system embedded in the concrete, there is no way that we can maintain it, or we can dig and I would say damage the structure, because as I said, the thermally activated structures, they have two functions: the mechanical function and as well as the thermal function, the thermal load. So if we approach the foundations, try to repair anything, I think this can affect the stability of the structure. So it wouldn't be possible. It's once we build the system, the pipes laid in the concrete, that's it. So we leave it, and I don't think we will need to at any point of time to excavate or make any changes, because it should be working. We'll be circulating coolant inside these pipes, nothing else. With regard to the second point, the initial capital investment as well as the return, I think it is beyond my expertise. This question might be better addressed to the government or to the industry. If we can, I'm sure if we can work together with the industry and enhance the efficiency of the system, the investment will reduce and the uptake will increase. But again, it's potential area to be considered, but it's out of my expertise.
I think this is a good time to perhaps give colleagues online a chance to listen to some questions, Anna.
Yeah. There is a question from Peter Walker, and he says, as these systems rely on rainfall to recharge the ground, how effective are they in dry parts of the country?
How effective?
In dry parts.
Okay. When we tested, I would say for our demonstration project in Dewsbury, there are two functions. The first function is when we divert the water to the ground, it will maintain the soil moist, and in this case, the thermal properties will improve. So this is in one hand, that once the thermal properties improves, the heat flux from the ground heat collectors to the surrounding soils will be better, and we can harness more heat and harnessing it faster as well. With regarding to charging the ground with heat, yes, we expected that when rain comes to the ground, it will bring energy. And from the data which we have collected, this was not something major. It did increase the temperature in the ground by almost 1 degree, which was temporary. It did not last for long. And of course, it is resulted in a slight improvement to the performance of the system. So it was 5% improvement in the system, although initially when we did the experimental work, we did expect higher improvements. But in reality, the system on site, I would say, improved by 5%.
There is another one, and it says, how compatible is diverting surface water runoff to the ground with sustainable urban drainage systems?
How
compatible?
How compatible? I think it is compatible because it is part of the sustainable urban management, that when we divert rainwater to the ground, it's, as I mentioned, it reduces the load in the sewer network, and also it reduces the likelihood of flooding. So it is better for the environment. Eventually, this water will go to the groundwater or to the water courses later on, but it will help us with terms of the management of our sewer resources.
Yeah, and the last one is, how do you control leaching of sand around BG array?
Okay, it's a good question. In this case, for the Westbury project, the infiltration trench was wrapped with geotextile, so that we prevent the leachate of, I would say, of any fine particles of water. And we had also wrapped the gabion wall in the back with geotextile layer, so that no leachate of sand, no wash out of the sand out of the ground. So the ground itself, I would say, the water will be maintained inside the ground. The only way it has to go to infiltrate downwards or laterally, and it will stay within the ground. So eventually, this water will go to the groundwater. So it is, but in terms of washing out of fine particles, I don't expect it. It did happen, or it will happen, because the permeability of the clay, the original ground, is lower. So there is no way for the fine sand to go anywhere.
Thank you for that. And I think if anybody's got any additional questions, I'm sure Mostafa will be very pleased to take them afterwards.
Is this question, Martha, sorry?
One more, maybe. Yeah.
One more.
It's obviously a big problem with heat pumps is the actual source of the energy. And with the increasing adoption of solar panels in the UK, I was wondering, is this a sort of package that homeowners should consider? Are solar panels a perfect complement to heat pumps, or do they work independently?
I'm aware that there is a research going in Newcastle looking at combining solar panels with heat pumps, so we can recharge the ground as well with energy, so that we store it down into the ground at the time when we need it. So yes, it is a great idea, Majd, and I think it is possibly, yes, we can combine the two systems.
Okay, one very final question there.
I just have some questions, Professor. What do you think about using thermal energy?
Yeah.
For developing countries, like,
for
developing countries, especially in Rift Valley areas of the sub-Saharan Africa, they have potentials of geothermal energy. Is there anything that you can plan in the future, some projects to do like that?
Yes, in fact, it is better to have harnessing geothermal energy from the Sahara of Africa. The ground temperature, it is at much higher temperature. We're talking about in the UK, the data which I have shown you, the temperature varies between 5 to 17. in the Middle East or in Africa would expect the temperature to go up to 25 degrees in the ground. So it is much easier to harness heat. You can harness more heat, and in fact there are some projects looking at harnessing the thermal energy for electricity generation. So we can use it, we can upgrade it, and we can use it to generate electricity. So the potential it is much higher in hot countries. Having said that, it is also, it can be used in temperate countries as well. So it's yes, it can be used.
Thank you.
Thank you. Thank you for all your questions, and I'm sure Mostafa will be happy to talk to you afterwards. I think it's been a very excellent evening. I think Mostafa has shown great skill as an engineer and as an academic speaker. He's managed to engage you all in a subject that most engineering students, and there are a few of them in the room, thermodynamic cycles and heat transfer, getting students to come to lectures on that is usually a big challenge, followed by getting the staff to actually give lectures on that topic. So excellent work on that front, Mostafa.
Thank you, Martin.
I think you've taken us on a real tour de force. You looked at the global carbon footprint issues and brought that right down to the local level, which is an excellent thing to do. You looked at heat pumps and again looked at those on different scales. What does it work best at? Our own homes, our individual homes, or on a district of a city? And that gives lots of questions to architects and urban planners. You then looked at the structural, thermally activated structures, which are very interesting, bringing us much up to contemporary now for materials for heat storage, conductive additives, and right up to phase change materials. So I think that's been an excellent overview of the subject area. What, over about 15 years, something like that? Yep, that's excellent. Right. So I think Mostafa's done a really good job this evening. He's a great colleague in the faculty. He's very well liked, not just for his disciplinary expertise, but also for his friendship and his interaction with his colleagues. For most of the time I've been at Bradford, which is 8 years now, he's been the head of discipline for civil and structural engineering. And he's shown the perfect blend of championing and passion for his discipline, which we've seen tonight, and also his compassion and dealings with people, be they staff or be they students. I think that's a great skill. Excuse me. So I think when he was promoted to Professor of Geotechnical Engineering, I was delighted on all those fronts for you, Mostafa, and I think you've given a great lecture this evening. So as we close, I'd just like you to put your hands together and give a warm-hearted thanks to Mostafa for his talk this evening.
Yeah. Thank you. Thank you. Thank you.